Today we're going to solve problem 5 from the 2022 USAJMO. It's a beautiful number theory problem that was proposed by Holden Mui. This one looks simple on the surface, but the trick is elegant. Let's get into it. Here's the problem. Find all pairs of primes PQ for which P minus Q and PQ minus Q are both perfect squares. Take a moment to think about it before we dive in. So first of all, let's name our squares. We can call P minus Q as A squared. And then we can call PQ minus Q as B squared. Now, a couple of quick bounds. Since P minus Q is greater than or equal to 0 and both are prime, we will need P is greater than or equal to Q. Also, we know that A squared minus A squared equals to P minus Q is less than P. So we will have 0 is less than A is less than P. And B squared equals to PQ minus Q. This is less than P squared because this equals to Q times P minus 1, which is less than P squared, because Q is less than or equal to P. So we also have 0 less than B less than P. And here's the trick. We can subtract the two equations. And then we'll have B squared minus A squared equals to PQ minus Q minus P minus Q equals to PQ minus P equals to P times Q minus 1. Factor to the left side and we can get that B minus A times B plus A is equal to P times Q minus 1. Now remember our bounds. We show that A is less than P and B is less than P. This will mean that B minus A is less than P. B plus A is less than 2P. So on the left side, we have a product of two positive integers. One is less than P and one is less than 2P, and it equals P times Q minus 1. Since P is prime and B minus A is less than P, the factor P cannot divide B minus A. So P must divide B plus A. But since B plus A is less than 2P, then the only possibility would be B plus A is equal to P. And then we can finish the proof by plugging back in P minus A equals to Q minus 1. Now, we know that P equals to B plus A, Q minus 1 equals to B minus A. Adding these, we'll have 2B equal to P plus Q minus 1. And then since P and Q minus 1 must have the same parity for 2B to be an integer, and P is an odd prime since at least for P greater than or 2, we will need Q minus 1 to be odd, which will mean Q is even, and the only even prime is Q equals to 2. So once we know that Q is equal to 2, then A squared equals to P minus 2, B squared equals to 2P minus 2. From B plus A equals to P and B minus A equals to 1, we can get that B equals to P 1 + 2. P 1 + 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 = 2P + 1 / 2. P + 1 / 2 and p minus 1 over 2 equals to a. So then we can check and see that a squared equals to p minus 2 gives p minus 1 over 2 squared equals to p minus 2. So p squared minus 2p plus 1 equals to 4p minus 8. Hence, you'll have p squared minus 6p plus 9 equals to 0. So for example, p minus 3 squared equals to 0. So then we'll have p equals to 3. So then we can have that the answer to this problem would be 3, 2. And that is the only solution. The key insight to solving this problem was subtracting the two square equations to get a factorization involving p, then using the size bounds to pin down b plus a equals to p. And from there, parity will force q equals to 2, and then algebraic will give us p equals to 3. So if you enjoyed this, smash the like button and subscribe for more Olympiad walkthroughs. See you in the next one.